Okay, so we started into something new today. Okay, if you have any questions as you're studying, bring them on Wednesday. We can go over them in class if you have some questions. Okay? So remember, exam is Wednesday at 3 o'clock. Okay? So you should have got a new outline sheet. Okay? This will cover the exam 3. Okay, that's way down the road. So let's get started into this stuff. Here we'll call this chapter Chapter 6B, and this will cover the second half of Chapter 6. Okay. And what this will cover are elimination reactions. Elimination reactions. Okay? So let's, for example, look at this molecule. Okay. And let's react it with OH minus, for example. We've already seen that one way this reaction can occur is for the OH to substitute for chlorine. So we'll call that our SN2 reaction. Okay, there are substitution reactions. Okay. But there turns out to be another reaction that can take place. And that's an elimination reaction, in that what can happen is we get an alkene, a carbon-carbon double bond. Okay? So SN2 and substitution and elimination reactions. You might ask, which product do you get? That one or that one? The answer is you end up getting both. Okay? You end up getting a mixture of the substitution and elimination. Okay? We didn't know that ahead of time, but you know it now. We just focused first part of the chapter on this. We're going to focus in on now how this product down here. Okay? So that's our concentration now for the second half of Chapter 6. How can these carbon-carbon double bonds form from reactions like this? Okay? So let's go ahead and set it up by looking at a model. Okay? Okay, here is our model. Okay, note that we are highlighting X, which remember what stands for halogens or leaving group. Okay, and note too, I'm showing the hydrogen on the carbon next door. Okay. Note that that is one carbon away, so if we call that the alpha carbon, this would be the beta carbon, and so we can call that a beta hydrogen. Okay. And what's going to happen is we're going to react this with a base of some type. Okay. And the base will end up giving us a carbon-carbon double bond between these two here. Okay? And so as a result, we're going to lose H and X, and so we call that elimination because they have been eliminated from this molecule. Okay? So you can write down any elimination reaction is going to give you a double bond of some type here. Okay? So we want to explore how this kind of thing happens. Okay? So we're going to explore the mechanism of this and start to open this up a little bit. Okay. If you remember in substitution reactions, we had two mechanisms, SN1 and SN2. Okay. Well, for elimination reactions, we're going to use E, obviously, and so we'll have E1 and E2 reactions. Okay? And we'll see that these parallel each other, SN1 and E1s, SN2s, and E2s. Okay? Let's look at these symbols a little bit so we understand what's going on. We didn't really talk about the symbols, but as you might know, S stands for substitution. The N, what do you think that stands for? Nucleophile. But we really didn't talk about these numbers. Let's talk about those numbers a little bit. Okay? So if I have SN2, that's what's called a bimolecular reaction. Okay? So that's what the 2 stands for. And up here for the 1, okay, that's going to stand for a unimolecular reaction. Okay. So what is the difference between a bimolecular and a unimolecular reaction? Okay. A bimolecular reaction means that 2 molecules are involved in the transition state. Unimolecular reaction, 1 molecule is involved in the transition state. Remember, SN1, there were 2 steps, weren't there? So you had 2 transition states. So this means there's 1 molecule involved in the what? Rate determining step of its transition state, which was what? The first step. Okay. So the first step, 1 molecule. Remember what's happening in that first step? The leaving group was leaving on its own. Remember that? Bimolecular, 2 molecules in the transition state. Okay? So this is often shown in the rate equation. bimolecular, the rate equation involves the concentration in one. The rate equation only involves the concentration of the substrate. Okay? The nucleophile is not involved in the overall rate. Okay? So if I change the concentration of either over here, the rate will be directly affected. Only if I change the concentration of substrate will this rate be affected in SN points. Well, these numbers match the same thing over here with E1 and E2 reactions. Okay? So the E1 is unimolecular and E2 is bimolecular. So they're going to follow pretty close here to the SN1 and SN2. Okay? So let's open it up a little bit and see how they do that. Okay, let's focus in on the E1 first. Okay? So we'll do E1 today, okay? Then focus on E2 next time. There's plenty with E1. All right? So how does the E1 mechanism proceed? Okay, let's look at this molecule here. So we have our substrate on the left and our base on the right. What is the tip-off? That it's SN1 or E1.
Remains on the alpha carbon.
Okay, so we need a little bit more.
And the beta carbon has the hydrogen and the base is
What's
reacting with
the tip-off that it's unimolecular? I got what kind of base? No, it's a weak base. Weak base. Why is that a weak base?
conjugate atoms.
There's no charge on it. There's no charge. And what's the other tip-off that this is SN1 or E1? A tertiary substrate. A tertiary substrate. Okay? So one possible product here would be the SN1 product. Okay, we won't look at its mechanism, but there's your SN1 product where this alcohol substitutes for the bromine. Okay. That product can form, and it does form, but we don't care about that product for right now. We want to get into that elimination product. All right? So what's the first thing that happens? The what? Leaving group leaves. It leaves. Okay? So let's cause it to leave. So if it leaves, remember we get a carbocation forming in the first step. Okay. In the second step, now this methanol, this alcohol is going to come into play. So let's bring it in. And if you remember, at the beginning, I said that this is going to act as a base. As a base, what does it want to attack? An acid or an acidic what's that? An acidic what? HCl. HCl has an acidic what on it? An acidic what? Hydrogen. Hydrogen. So this thing wants to attack, but it's going to be a base, attack an acidic hydrogen. Well, if you look, I've highlighted these two, what? Beta hydrogens. Okay? So I must have done that for a reason. Yes, the reason is these turn out to be acidic. How is that? Well, remember this carbocation, it's pulling electron density toward it. And it's going to pull even from these hydrogens. So it's going to make the hydrogen electron deprived, and so have a delta plus on it. Okay. And so that's going to make this hydrogen acidic. Okay, so I could use the bottom one, or I could have used the top one. So now my base will attack the acidic hydrogen. Okay. Oh, that paper shuffling going on back there.
Oh, sorry.
And these electrons will dump into there to form a double bond. Okay. You taking notes or are you working on something?
No, I'm taking notes.
And so we end up forming that alkene there. Okay, so that's how we get the elimination product having formed. Any questions on that? Okay, so something a little bit new. Okay, so here we're learning that the beta hydrogen has some acidic property to it. Okay. So if this thing would have added on the carbocation, it would have acted as a nucleophile. But here, it's attacking beta hydrogen, so it's acting as a base. Okay. Any questions on that? Is there another product it could have formed? What's that? Is there any other beta hydrogens?
Yeah.
Yeah, where, right here? And right here. So I could have formed a double bond here or here, okay? So we better draw those in. So So there would be another product, okay? So we need to make sure we're looking for all of our beta hydrogens. Okay. You could put the double bond here, but it'd be the same thing as this product. So we'll just keep it there. Okay. Any questions on that? Okay, so this is getting a little bit involved for us. Okay. Let's look at another example of the E-mol. Okay, let's look at this example here. See if we can draw the mechanism for that. Okay, so you should be able to do the first step there. What happens in the first step? Leaving group leaves. So let's draw that carbocation. So we get that. What kind of carbocation is it? Primary or
Secondary.
secondary? Okay. Well, here, the molecule is going to play a trade game. Did you ever trade or something? We all trade. Okay. What's the biggest trade you do every day? Money. Okay, you have $5, for example. $5 is pretty valuable to you. But you turn out to be hungry. And say, wow, I need something to eat. So you go to the store, get a pizza or hamburger. And now you give that $5 away. So what have you done at that point? You traded, but you have what? Counted that pizza as more valuable than your $5 bill. And so you trade. That's the only way you trade, isn't it? Is if what they have is more valuable than what you have. Or else you wouldn't do it, would you?
Right.
No. Okay, that's the way you make choices. Whatever is more valuable to you, you'll make that choice. Okay. Well, here, this thing can gain some more value. It says, look here, I'm secondary, but next door, if I could trade this hydrogen to there, I can move my positive charge here, which will become what? Tertiary. Think it'd like to do that? It'd love to do that.
Yeah.
Okay. So it gained stability. It gained stability. This is what's called a carbocation rearrangement. Okay? Where it trades a hydrogen for a more stable positive charge. Okay? So if I go from secondary to tertiary, it would love to do that. There's two ways it can perform the trade. One way it can perform the trade is with a hydrogen, like we did here, okay? So this hydrogen moved from here to there. The other thing it can trade, okay, we'll see in a later example, is a methyl group. So you can get a hydrogen shift or a methyl shift in this carbocation rearrangement. Okay, obviously would not want to trade a methyl because then that would make it secondary. So it trades the hydrogen. Okay, we'll see a case of CH3 later on. Okay, so now once that carbocation rearrangement has occurred, now I can continue on. Now my alcohol could do an SN1 and give me the SN1 product. Okay, which is from the rearrangement. We didn't look at rearrangements earlier, but now we can see that they occur. Or we could go on to the elimination product. Okay, where now the alcohol takes the acidic beta hydrogen to get that there. Is there another possible product?
Yep.
Okay. It could have taken one of these beta hydrogens. Give you that one there. Okay. So again, something a little different here with these eliminations. Any questions on what's going on here?
On the test, I mean, not this test coming up, but the next test with elimination on it, would you want us to put to both possibilities on it?
Yeah, I'll actually develop those questions more as we go into E2s, okay? But for now, yeah, just assume that I would want both. Yeah. Okay. All right, well, let me give you two examples and see if you can work these out, okay? This will be right from your homework problems. Okay. see if you can do these problems. Okay, just do the E one here. See if you can do that one. Okay, so work on these, and I'll be calling you up here, so better be ready. Also a good exercise in being able to draw out the molecule from the name. Okay, so I need a volunteer for the first one. All right, come on in. They're right underneath. These are gonna dump into there. That's good. They're all the same. That's good. You can have a seat. Okay, good job. So she got this right, okay? She put the double bond on this side, but note the molecule is symmetrical. So whether I have the double bond there, there, or there, it'd all be the same product, okay? Note that carbon is what? And a non-chiral carbon, okay? You got three same groups there. Okay. All right, so that's that one there. Anybody want to give this one a shot? A little more difficult. Okay, can't have the same person. Okay, can't have a chalkboard hog. Okay. Looks like Pew's confident back there.
I don't even have it down.
I'll try it.
Okay, we're running out of time, I better do it. Thanks for your,
I'm fine.
thanks for being a volunteer, though.
Is this the method switch right here?
So, let's start here. We got butane. Got two methyl groups on the second carbon. This here. So we can have the bromine leave. And that puts the positive charge on that carbon. Hopefully you got to that stage. Okay? But then, what do we have next door? I can trade this time a methyl group. Okay, so I can do a rearrangement here. So that'll move the carbocation over. now give me tertiary. Okay, so here it's secondary. And now I'm more stable at tertiary. And then lastly, I can do the attack at the beta hydrogen. And form the alkene. Like that there. Okay. Obviously, you get the other product attacking one of these beta hydrogens. So we'll draw that up here. Anybody get either one of those? Okay, a couple of them, good. You get it? Okay. So, this is our introduction to elimination reactions today. Okay. And we'll pick up more on these on Wednesday. We'll see you then.